What was type 1 error?
Rejecting the null.
Rejecting the null when it's actually true. Type 2 is
Rejecting the null when it was actually accepting it.
accepting the null when it's actually false. Okay. So what we're going to start doing now is actually getting into the hypothesis testing itself. Not just talking about what it means, but actually doing it. The first things on here are some things that we already know because we're talking about a lot of the same variables that we've already done. For instance, on our last test, we talked about p hat. We know that p hat is x over n. We know it is normal with the mean and standard deviation. That is all on your formula sheet when we talked about it before. We were able to use all of our strategies if the n times p times 1 minus p was greater than or equal to 10, and it was less than 5% of the entire population. It also had to be a simple random sample. It has to be random, but the two conditions that I really made you check over and over again were that it was less than 5% of the population and the greater than 10. So we're continuing to talk about the p hats, and those assumptions still have to be true in order for us to do the things that we need to do. We'll talk about statistically significant. What that means is the results are unlikely under the assumption that the null hypothesis is true. Okay, the null hypothesis, that's something I am going to assume it's true unless you tell me it, unless you can convince me otherwise. So if I am assuming something is true, and under that assumption, you find out that the probability of whatever occurring is 0.005. So there is a 0.5% chance that it would actually happen if my null hypothesis was true. Then would you believe my null hypothesis? No, because it would be very, very unlikely under those conditions. That's what we're going to be doing. We're going to assume something is true. We're going to calculate the probabilities under that assumption. And if we get a really small probability, then we would assume that the null is probably false. We would reject it. If we get a 32% chance, would you reject my null hypothesis? No? I mean, it's maybe not extremely likely, but it's not unusual. So you would accept it. You would leave my null as it is. So anything that's, if it's statistically significant, that's when we reject the null. Now, what it means to be statistically significant is going to vary from situation to situation, because in some cases, it's more serious to make an error than others. If I were trying to decide how much my statistics students study each week, do I have to be extremely accurate there? Not really. So even if I did, a 10% level, that's not a big deal. But if you were trying to figure out if a new drug was successful at stopping a stroke, would you want a 10% chance that that was wrong?
Not really.
Not really. So you have to look at the situation to decide what is significant or not. For now, I'm just going to be telling you alpha is 0.1, alpha is 0.01, or whatever. And that is the level that we will be using. Okay, so let's look at this. A researcher obtains a random sample of 1,000 people and finds that 534 are in favor of banning cell phone use while driving. So that's our p hat, 534 over 1,000. Does this suggest that more than 50% of people favor the policy? Or is it possible that the true proportion of voters who favor the policy is something less than 0.5, and we just happen to get a sample where they were in favor? So we're trying to decide, do I actually believe this or not? Is this convincing that more than half the people do, or is it not? So we are trying to decide, would it be unusual to obtain a sample proportion of 0.534 or higher from a population whose proportion is 0.5? Okay, we'll be looking at problems like this, and the first step you always have to be able to do there is the null and alternative hypothesis. Okay, we have to figure out what the overarching question is, and I'm trying to decide, does this mean that more than 50% of people favor the policy? So what is my parameter? Is it mu, sigma, p, what? P. I'm talking about proportion. So our null is always this parameter equals something. So what would I start out saying? P is 0.5. The alternative, I'm trying to decide if P is greater than 0.5. Okay, and you would need some way to go about this. You know, if you look at lawmakers, they don't want to put something on a ballot that they know is absolutely going to fail. They want to see, is it worth our time to try to convince people to vote for this or not? So they might be looking at something like this. Now there are different approaches we can take. There's what's called the classical and the p-value approach. For me, I'm going to talk about both and I will show you both. Most of the time I'm going to stick with the p-value approach. It's a little more precise. But we do need just kind of an understanding of what the classical one is. So basically, this one is measuring in terms of standard deviations. If your sample proportion, so if P is too many standard deviations from the one in the null, we reject. You know, if you think about just like a normal curve. You know, here is your mean, and then we've got, this is your mean plus 1 standard deviation, and your mean minus 1 standard deviation. As you get further away, what happens to the probability of things happening?
Well, more and more because they have to do it.
Well, okay, so yes, but if I wanted to like think about the probability just being up here,
Oh.
that gets smaller and smaller, right? So if you're too far away from the mean, then we would reject. If you're close, then it's still likely we wouldn't. Okay. So going back to my question, let's just use the researcher question that I had. If I were going to talk about the probability model, if I'm going to do anything, I need to know, is it normal or not? So that's my n times p times 1 minus p greater than or equal to 10. That's what we have to do to decide if it's normal. My n, how many people did we survey? 1,000. P, we are trying to, you have to be a little bit careful. There is a p hat in this problem, and then the p is the 0.5. So we are going to be using the 0.5 here. $250. Which is more than 10. So yes, it's normal. Approximately normal. We can find the mean and standard deviation. You did it on the last test. It's on your formula sheet. We know the mean is just what? It's just your p. So the p that we are using is 0.5. We're not talking about the p hat yet. The p hat is the one we will be testing against. So we're just using our mean of 0.5. Standard deviation. Okay, so that is when we did our square root of p times 1 minus p over 1,000. And we can leave a lot of decimal places. I'm just going to, for the sake of this example, I'm going to round it to only 3. So that's all old stuff. We did it in the last test, last chapter. In terms of the curve, if I were measuring, the P is my center here, so that's your 0.5. A standard deviation is 0.016, so one standard deviation above would be 0.516. One standard deviation below, so 0.5 minus 0.016. So then I would have to tell you what's it going to take to reject the null. And that isn't necessarily something you decide. For now, that's going to be given to you. So I might say, you know, this is really serious. I don't want to reject if I shouldn't. It has to be 3 standard deviations away. Or I may say, it's not really as big of a deal. Maybe 2 is sufficient. So I would tell you some measure. So for our example, I'm going to reject if it's more than 2 standard deviations away. You know, if you think about the empirical rule, we expect 68% of the data to be within 1 standard deviation. How much was it within 2?
95.7. There's a 7 in there.
Empirical rules on your formula sheet.
95.
Yeah, 95, and then the third is 99.7. So, you know, within 2 standard deviations, I would expect that to happen 95% of the time. So it's not extremely rare. You know, it's not unusual yet to be outside that, but it is definitely less common.
So if it's really serious, it has to be 3, because you know all of it.
Yeah, you would want to be much more.
And then if you don't really care, then it can be 1.
Yeah, we would probably never do 1. We'd probably stick with 2. Okay, so let's find the z-score. So z is our x, which is like our p hat in this case. What was the p probability we observed? 0.534. Minus the p that we're using, which is 0.5, so minus mu, over our sigma, which is 0.016, which we know if we wanted a better answer, we should probably have more decimal places there, but for this, I'm going to let it go. Okay. So what this tells me is our data is 2.125 standard deviations it's positive, so above the mean. So a z-score is just like how many standard deviations. We said if it's more than 2, I will reject my null hypothesis. So do I reject it? Yes. Now, if I were going with 3 standard deviations, could I have rejected? No. We could, you know, if you wanted to think of this in another way, if I wanted to do the probabilities, the probability that my z is greater, I said 2 standard deviations. So let's just do that. Let's see how rare it actually is. 2 standard deviations away from the mean. So if you go to your normal table, when my z is 2, what do you get from your table? Yeah, and to do greater than, you would do 1 minus. So the probability of being more than 2 standard deviations above the mean, there is only a 2.28% chance that you would be above that 2 standard deviations. So if I'm 2.1 standard deviations, I know there's less than a 3% chance that that happens. So is that unusual? Yes. So that is kind of like tying it back into what we did before. If you're looking at the probability, that is unusual. So we reject So that's just kind of another way to support the decision that we made. Okay, that's the classical idea. The second option is the p-value approach, and that's the one that I will use more often. So let's talk about it. In the p-value approach, basically what we look at is what's the probability of this happening if my null hypothesis is true, and if that is smaller than the level I have set, we'll reject. Okay, so just something, I'm going to talk about this a lot, so it would be very important to know what a p-value is, because I'm going to talk about them over and over. When I talk about a p-value, it's the probability of observing a sample statistic as extreme or more extreme than the one observed, if the null is true. So basically, it's just the probability of that thing happening, under the assumption that the null hypothesis is true. So if our p-value is really, really small, that means it's really, really unlikely to happen if my null hypothesis is true. That means I reject. All right. So in our example, right, if I measured 2 standard deviations, we did 1 standard deviation before. If I added 0.016 again, I get 0.534. Well, not exactly. If you had a few more decimal places and rounded appropriately, that's what it would be. So if I wanted the probability of being greater than that. Okay, we found our z. So we've got the probability that our z is greater than, what did we get before? 2.125? If we're going to go to the z table, we have to round to 2 decimal places, so we'll go to 2.13. So if I just want to measure that probability of that occurring, greater than is 1 minus. If I looked up 2.13 on my table, I get 0.9. So there is a .0166. So that's the probability of having above that 0.534 that we observed for our p-hat. So there is only a 1.66% chance that this happens, so that's unusual, we would reject. Are you guys kind of understanding the idea of what it takes to reject? So we're looking at the likelihood. If it's really small, then we reject. If it's not, we don't. So this is kind of our general trying to wrap our minds around it approach. We're going to talk a lot more now about if I want to be a little more precise about it. So our first step is always the null and high alternative hypotheses. Same 3 options that we talked about yesterday. The null is always equal. Alternative can be not equal, greater than, or less than. Step 2, we'll have to have an alpha. Most always for now, it will be given to you in the problem. And basically, the more serious it would be to make a type 1 error, which type 1 is what? Rejecting when I shouldn't. So the more serious it would be if I rejected when I shouldn't, the smaller that alpha will be. If it's less serious, we can use a bigger alpha. Okay. Then we are going to find our test statistic. We are looking at our z-value. That looks really confusing, but it's similar to everything we've been doing for our z's. You know, we wrote it as x minus mu over sigma before. Basically, right now we're talking about sample proportion, so it'll be p hat, what we observed, minus the mean over standard deviation. And then we'll talk about our critical values. So we'll have to look at, if I'm talking about a two-tailed test, then I'm going to have to split my alpha up over the two tails. So if I had a alpha of 0.5, I would have to do 0.025 because I would have above and below. If it's just a one-tailed test, then you keep the alpha that's given. So we have to know what kind of test we're doing. And then we would compare that. Now that's the classical approach. The p-value approach starts out very similar, except we will actually just, we're going to compute our z still, but then we're just going to say, is our p-value smaller than alpha? If it is, we reject. So this is the approach that I am going to go with more often. And then I would like at the end for you to state the conclusion. If there is sufficient evidence to reject the null hypothesis, or there is not sufficient evidence to reject. Okay, so now we are getting into examples. And I printed these for you, but you might need a little extra space. So if you write big, you might want to get another sheet of paper. This one I'm going to do both ways. I'm going to do the classical and the p-value, just to show you the difference. And then after that, I'll probably stick with the p-value approach. Okay. In 1997, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In a 2007 poll, 1,010 adults nationwide, 525 of those say they did not trust the media. At the alpha equals 0.05 level, is there evidence to support the claim that the percentage of Americans that do not trust the media has increased since 1997? Okay, we should check our criteria here, because did it tell me that this is normal? No, so let's do a quick check that our n, p, 1 minus p, greater than or equal to 10. My n, how many people did we talk to?
1010.
The p is the assumption, what we started with. So we are talking about the original, so the 0.46. So if I do that, that's bigger than 10, isn't it? Good. 250.88. So that's good. We can assume, would 1,010 adults be less than 5% of the whole population? Yes. So our criteria is met. So let's kind of walk through the steps. The very first thing you need to do, yeah, they start out the same. So I'm just going to do those, and then I'll branch off and show you the two options. So we always start out with the null and alternative. So we're talking about the percent, so that's my p. The null would be p equals. I am trying to decide if it has increased. So my alternative would be that p is greater than 0.46. Okay. If you look back at the steps I told you, step 1 was the null and alternative. Step 2 was your alpha, which is just given to you, so you just need to be aware. My alpha here is 0.05. Step 3, we are actually going to compute some things. So this is where the approaches start to get different, but either way we have to compute the test statistic. So my z. We need some things before we can plug into that formula, don't we? What is my p hat that I observed in this? We had 525 out of the 1,010. Okay. We need our mean, which the mean is just going to be our p, so 0.46. We need our standard deviation, which is the square root of p times 1 minus p over n. And hopefully this stuff is really familiar, because that's what we did on the last test. And we get 0.01568. Okay, so now I can actually do my z. So z is your p hat minus your mean over your standard deviation. Now let's talk about our two approaches. So the classical approach involves probably the thing you guys have struggled with the most here, your Z alpha stuff. Now, was this a one-sided or a two-sided test? It was just one-sided. So I don't have to do alpha over 2. I'm just doing Z alpha. My alpha was 0.05.
You don't have to do that.
Only if it's a two-sided test. So you would have to go to your normal table then. Okay, so remember, how do we look this up in our table? Right, we have to find our area inside the table. This means the area to the right is 0.05, so our table tells you the area to the left. So you are looking for 0.95 inside the table, and then telling me the Z on the edge. So that is 1.6. So that is my Z. Okay, then we compare the Z we got versus this one. So this is our baseline. Our Z was 3.83, so that is bigger, so it's more standard deviations away, if you want to think about it that way. Since that is bigger, you reject the null hypothesis.
So why would we reject that at 3? Because they said it was supposed to be bigger than 3, and since it wasn't bigger than 3, but if that was a different way, like they said, it was going to be less than that.
So basically, at the 0.05 level, we found that 95% of the data should be the 1.645 or below. We got something bigger than that, so it's outside that window, so we reject. Now, my preference, I like the p-value approach. If we're looking at the p-value, we are going to find the probability of our Z, just like we used to do. Everybody with me? So I want the probability that my Z, we are trying to, our null was being greater, so I want my probability Z is greater than that, which we got 3.83. So greater than is 1 minus. Can you even read a 3.83 on our table? No. The highest our table goes is 3.49. So we know at the very, it's even going to be smaller than this. So I'm just going to put the biggest number my table goes to because it doesn't go up high enough. So the probability that this happens is actually even going to be less than that. So this probability is less than, what was my level of significance in this problem? 0.05. Okay, what that means is if the null hypothesis is true, if the true probability is 0.46, the probability of getting the result we did is 0.02%. So if that's true, this is extremely unlikely. So that would tell me reject the null hypothesis.
So the bigger the bigger number you find in here, the better it is.
Yes. So my conclusion would be there is sufficient evidence to conclude that, what was even the question? The proportion of Americans who don't trust the media is more than 0.46. So we reject the null. We have evidence to prove it is more.
Do we have to use, like, does it matter which one we use to do our homework and test and stuff?
We'll probably stick with p-value because I'm going to show you can actually use your calculator a little bit for the p-values, so it's nice. Alright, so would you guys like to know how to do that on a calculator? Okay. So, on your calculator, if I wanted to look at example 1, you are going to go to Stat, Tests, and we are looking at number 5. The one proportion z-test. Okay, it asks you for your p sub 0. That's like our beginning proportion, which is 0.46. It asks you for the x. Think about when we do p hat, we do x over n. How many Americans said they were in favor on that example? So our x is 525. Our n, how many people did we talk to? That was 1010, wasn't it? Okay, then you have to pick which thing were we testing. Were we testing not equal, less than, or greater than? So you're going to go over to greater than, select it, and then do we want it to calculate something or draw us a picture? Calculate. Okay. When you do that, your calculator tells you a p-value of the p it has, mine has the like 6.8586, e is a -5. That means you would move your decimal back 5 spots. Now, why is that not the same thing we got from our table? Yeah, and did our table go up high enough for us to actually get the number? No. So if the number had actually been on our table, these would match. But either way, we can tell this is most definitely smaller than 0.05. So we would reject our null. So one of the big benefits of the p-value approach is you can use your calculator to help you do all this stuff. I've shown you how to do it by hand, but we also have that option. All right. Questions there? Let's do another one. Okay, when asked, is it more important to protect the right of Americans to own guns or to control gun ownership? 46% of all Americans said protecting the right to own guns is more important. A research center surveyed 1,267 randomly selected Americans with at least a bachelor's degree and found that 559 believed protecting the right to own guns is more important. Does this result suggest the proportion with at least a bachelor's degree feels different than the general population? Okay, so first we should check the criteria to make sure this is normal. So my n times p times 1 minus p. My n, 1,267. My p, what are we using here? 0.46. 1 minus 0.46. And that gives me 314.7, so that is most definitely greater than 10. That means it's approximately normal. Would 1,267 be less than 5% of the population? Yes. So we can move on. Null hypothesis is that our p is 0.46. Alternative hypothesis, we want to know if they feel differently, so does not equal. All right, what alpha level were we given? Okay. So, How do you want to do this? Do you want to try it on a calculator? Okay. I may do it by hand as well, just to show you, but we'll start with, if you want, on the calculator. So you go stat, test, number 5. My p-value here is 0.46. I'm creative. Same thing twice. My x value, when I'm finding my p-hat, how many people said yes, they believed? So my x is 559. My n, 1,267. My proposition here is not equal. And what I get, and it tells me that my z value is negative 1.34. And it tells me my p, the probability of that happening, is 0.1794. So under the assumption that the proportion is still 0.46, there is a 17.9% chance that this occurs. Would I reject my null hypothesis? No. I'm only going to reject it if it's less than 0.1. So this is not less than 0.1, we would fail to reject. I think I have time to real quick do this by hand and show you, and then I'm probably done for today. So, to do it by hand, we need several things. We need our p-hat, which is 0.4412. We need our mean, which is the 0.46. We need our sigma, which is the 0.46 minus 0.46 over 1,267. Okay. Then you have to calculate your z value, which is your p-hat minus your mean over your standard deviation and I get negative 1.34. Look familiar? That's the value that our calculator found. The trick here is the z alpha part. Basically what this means, here's negative 1.34, this is positive 1.34. Because this is a two-tailed test, we actually have to do both of these. The curve is symmetric, so what we could really do is just find this one and take it times 2. So we're just going to do 2 times the probability that z is less than negative 1.34 because we have two tails. So if you go to negative 1.34, multiply those and we get 0.1802 for my probability. Slightly different because this is more accurate. Our table, everything is rounded, and your calculator does it more exact. But either way, this is bigger than the 0.1, so we fail to reject. There is not sufficient evidence to conclude that it has changed. All right.